In order for us to develop the normal density function, the first thing that you need to do is enter all of these data. These are the ages at inauguration of the 45 presidents of the United States. These need to go into list 1. You should store them then into the list titled Prez, P-R-E-Z. So you should also set this window and get the histogram graphed on your graphing calculator. If you haven't taken the time to do that, pause the video, get the data in, save it, set your window, get the histogram on your screen, and we'll go from there. So this is what the histogram should look like. So when we look at this, something to think about, here's the window setting from 40 to 74. That accommodates the minimum and maximum values in the data set. We have a scale of 2, so our class width is 2 years. The Y minimum and the Y maximum just let us see the bars acceptably. And then if you press second Y equals, we should have plot 1 on using our data from list 1. It should be set to a histogram. If you're getting an error, you want to make sure that the other 2 plots are turned off. You also want to make sure that your data is in list 1. So having said that then, if we wanted to describe the shape of this distribution, I would certainly say it's symmetric. I would certainly say that it's mound-shaped. So the idea of it being symmetric is probably the most important idea. So this is relatively symmetric. And I guess mound-shaped. So it's tallest in the middle and it trails off to the sides. So it shouldn't be a problem for you to run one variable statistics. So we're on the graphing screen. If we press second mode, that will take us to the home screen. Stat, calculate, there's the one variable statistics command for our data in list 1. So to the nearest tenth, notice to the nearest tenth, the mean is 54.97, but that 7 is going to push the 9 up to another ones place actually. So it's really 55.0. That's the mean to the nearest tenth. There's the standard deviation, it's 6.6 years. And if we scroll down, the median is 55. So here's where we are. So the mean is 55.0 years, the median is 55 years, and the standard deviation is 6.6 years. So what do you notice about the mean and the median? Why does this make sense? So if you look at those, they're almost identical. They're incredibly close. So again, this is rounded ever so slightly, but they're very close. Why does this make sense? It goes back to the shape, because this is a symmetric distribution. They're quite close. Because the distribution is symmetric. So now, I don't want just a symmetric distribution. I'm trying to find a function that I can use to model this distribution. So I don't expect you to put this into your y equals menu, but I have this prepared where I have a special function already put into the y equals menu, and I'm going to show you what it looks like. So again, you don't have to put it in. I already have the function in there. I'm just going to highlight the equal sign and press enter so I can turn that function on, and I can lay it on top of the graph. So this function right here is the normal distribution. I am graphing a normal distribution with a mean of 55 and a normal distribution with a standard deviation of 6.6 from that mean of 55. And notice, the normal distribution does not fit the data perfectly. Sometimes, like at the peak, the data pops outside of the normal distribution. Here, this bar of the histogram is quite low compared to the normal distribution. Here, we nailed it pretty closely. So again, it is not a perfect fit. A mathematical model is not meant to be a perfect fit. It's an approximate fit. So it's important that you use that word when you're describing what you're doing. So bear with me a second. So here, this function is the normal distribution. So now, in order to make it not just the normal distribution, but to make this a density function. So to make this a density function that's compatible with any data, not just the presidential data, but I want this to be compatible with any mound-shaped symmetric distribution that looks like this one, what we should do is standardize the data. In other words, we should be using z-scores. So we're going to standardize the data, meaning use z-scores. And what I'm going to do is actually change all of the president's ages at inauguration. I'm going to turn them all into z-scores by using the following command on the home screen. So I'm going to take every value in list 1. I'm going to subtract 55. I'm going to take that quantity and divide by the standard deviation. And I'm going to store those values into list 2. So let's create all of those z-scores in one shot. Second mode takes me to the home screen. So my ages are in list 1. I'm going to subtract the mean of 55. I'm going to close the parentheses, divide by the standard deviation of 6.6, and I'm going to store this into list 2, second 2. So, for instance, I can see here on the screen the very first z-score is for George Washington. George Washington was 57 when he was inaugurated. The mean is 55, so his age at inauguration is 0.3 standard deviations above the mean, ever so slightly above the mean. So what I'm interested in, though, is looking at the characteristics of the z-scores. So the mean of the data set is 55. The standard deviation of the data set is 6.6. But now that we've changed to z-scores, I want you to see what the mean and the standard deviation of the z-scores are, and then we'll explain that. They have a very convenient mean and a convenient standard deviation. So we've stored everything into list 2. So I'm going to run the one variable statistics command on list 2, second 2. Here we go. Notice what's happened then. We have a mean of negative 0.003. For all intents and purposes, this mean is 0. And then down here, look at the standard deviation. The standard deviation for all practical purposes is 1. The mean is 0, the standard deviation is 1. And the reason they're not exactly 0 and 1 is because we rounded the mean to be 55, and we rounded the standard deviation to be 6.6. So even with that rounding, the mean for the z-scores for all practical purposes is 0, and the standard deviation for the z-scores for all practical purposes is 1. And we can actually explain that by thinking about the transformations that have been done to the data set. So the mean and standard deviation of the z-scores to the nearest whole number. The mean is 0. The standard deviation is 1. In fact, if a data set is standardized without rounding the mean and standard deviation, we rounded. If you don't round the mean and standard deviation, 0 and 1 will always be the mean and the standard deviation for z-scores. So here's the reason why. Up here, here's my data set. Subtracting 55. Will that change the mean? Sure it does. So what we've done is we took a data set with 55, we subtracted 55 from all of the values, so we shifted it left by 55 units. That's made the new mean 0. Dividing by the standard deviation will also affect the data set, but if you take 0 and divide by 6.6, you still get 0. A mean of 0 for your z-scores. So now something important to think about, subtracting by 55 will not affect the standard deviation, but dividing by 6.6 does affect the standard deviation. So when you take your data set and divide everything by 6.6, you're taking the old standard deviation for the data set in L1, which was 6.6, you're dividing by 6.6. Well, 6.6 divided by 6.6 gives you a standard deviation of 1. So the idea is if a data set is standardized without rounding the mean and standard deviation, you always get 0 and 1 to be the mean and the standard deviation for z-scores. And that's really, really useful because what that means, anytime we think we are using normally distributed data, when we calculate z-scores, no matter what the context, we can work with a mean of 0 and we can work with a standard deviation of 1, which are incredibly simple to work with. So in the next video, understand what we've accomplished then. We are not just creating a normal density function. What we are going to create is a function called the standard normal density function. The standard normal density function. It's not just the normal density function, it's the standard normal because we're going to specifically work with standardized scores, with z-scores. And we'll see in the next video that we really do get a density function, and it'll come up with some patterns that you have seen before and will find really useful.